Hi, this is a demo video for my power supply project that I've been doing for some time now. It is basically a spin-off of the power supply project done by Dave Jones of the EEV blog. I got to learn a lot of things from those posts, and I did a few modifications to his schematic, and I got this. Of course, it's still not perfect. I am still learning from it. So one of the differences between his last schematic and this particular device that I've prototyped is that instead of using a 2.048 volt voltage reference, I'm using a 4.096 volt, so that I can basically take advantage of the entire 5 volt range of my ADCs. I am using the ADC on the Atmega. So I have my output stage particularly in one location. Instead of rotary encoders, yeah, I wired up the rotary encoders as well, but I'm using buttons in this particular prototype. You can see that the footprint actually overlaps the footprint of a rotary encoder. So I could do that on a different prototype, but I just chose to use cheaper buttons. And instead of using an I2C LCD, I have an MSP, a microchip part, which is basically an I2C to parallel I/O converter, and of course that's used to run my LCD as well as take in some interrupts and stuff like that. I have, of course, the same 1 ohm. Instead of using 10 ohm resistances, I'm using 1 ohm resistances. Probably that's a bad idea. And of course, the same problem with Dave Jones's design. I'm using LM358, so these are not actual rail-to-rail op-amps, so I won't be able to get the 0 volts, and there's going to be some problems at the lower end and the upper end of the spectrum. For this particular design, I'll be sharing the schematic as well. Before I do that, of course, I have my this is in the output stage, the voltage reference. This is again a microchip part. This little thing, that's the DAC, and of course the LM358, and I have a gain of 5 set in this particular case for that. The current sense amplifier, of course, in order to sense the current, and I haven't actually gotten around to writing the software for sensing and calibrating the whole current being consumed, because of course it's going to be taking some current to make the system run as well. So that software has not been done yet, but this is just the first revision for the software, but the third revision for the hardware. And not a big difference, but I am using a wall wart adapter. Now this is not a DC adapter that you find. It's actually from an old modem. So it's the output, the secondary of this thing is actually 12 volts 1 amp AC instead of being a DC output. So I have the rectifier and the filter cap, as well as the switch on the PCB itself. I didn't design it for any particular kind of enclosure, so it's just the minimum packing that I could do, and to reduce the cost of the prototyping PCBs. I have a 5 volt regulator. Of course, it's taking a little more than 12 volts, and I should have used a switching regulator, which I'm going to do in version 4.0. But in this case, I need a heatsink for that. And of course, I have an LT3080. I was not able to get precision resistors for this particular prototype, so I had to improvise with some other stuff. And we'll see in the demonstration that because of the imperfections in the resistances, I'm not able to get the exact gain of 5, and the corresponding values are not exact. Alright, powering it up. So it starts up with 0 volts as the output and a 500 milliamp output limit. This is the measured current consumption. Of course, that's not been set right, and of course there are problems with the voltage not being, it can't be set to 0, because of course if I probe the set pin of output, so it still says 0 0, but the output of the op-amp is not, of course, 0, because it's not a rail-to-rail op-amp. Alright, I've set the voltage to 1.02 volts in software. So if I probe the set voltage, you can see it's 0.2. So because it has a gain of 5, so I should be able to get a voltage of 0.2 multiplied by 5, that's 1 volt, but the display says 1.02. That's because I compensated for the gain of the op amp in the software itself. So you can see that the output says is 1.01, 1.02 volts. Of course, these are not very high accuracy DMM, so there's going to be some error in the multimeters itself as well. And now I have set it to 3 volts. So if I take a look at the gain here, 0.6 multiplied by the gain of 5, I should be getting 0.6 multiplied, so it should be 3 volts exactly. Of course, it's now showing 3.02. The offset has been cancelled in software, and things start to run off. So it was actually calibrated. The offsets I did in software are for a shorter range. I'll have to make the modifications in the software, but more or less you can see that the output is quite precise. It's 0.6 volts for 3 volts, and if I multiply it by 5, I should be able to get exactly 3 volts on the LT3080. Taking a probe on after a gain of 5, you can see that I have a 3.02 volt set from the op amp's output, which is being fed to the set pin of the LT3080, and that's why it's basically producing 3.0 volts, just 3.02 volts on the output side of the LT30. And of course, we have the set voltage of 4.99, which means I have exactly 1 volt set at the output. Of course, the offset is again kicking in there, multiplying it by a gain of 5, so I should have a 5 volt output. And well, amazingly, the op amp actually gives the right kind of gain, and it's about 4.995. So yeah, so that works out. The LM358 doesn't. I think I heated it up a lot more than I should have, and I soldered it on, so it's really not showing me some linear properties. So I think it's attributed to that, or maybe it's something to do with the power supply. Of course, I'm using a the VCC for the LM358 somewhere around 12 volts, so it's operating in the right range, but somehow the op amp is not working in a linear range. Of course, it could be the feedback resistors and them being MFR, not CFRs. Sorry, being CFRs and not MFRs. So that could have something to do with that, and my bad soldering, of course. Alright, setting it in software to 9.99 volts. The output is of course 2 volts multiplied by 5, and that should be about 10 volts. It's about 9.99. That 9.98, 9.99, it just bounces around, so you can see it's 9.97, 9.98, and the LT80 follows that particular voltage. It's 2 volts exactly here, so there is some offset in the I've already done some offset in the software part as well. I could probably do an algorithm where I can step from all the voltages, read how much output it's actually creating, how much it's supposed to create, map out the errors like a lookup table, and then that could actually be used to recalibrate the power supply every time, or maybe every once in a while, and that could do it. And of course, if I connect a load, I've already set it to about 304 milliamps, and it's already reading a 141 milliamps. So if I connect a load resistor, you can see, there we go. So you can see that there are two things happening here. One of them is that obviously the voltage drops, and you can see that it's reading there's a load current consumption, and then there is the LED which blinks. Oh, nothing got hot. Okay, so the LED blinks because that means it's actually cutting and limiting the current, and because it's limiting the current, it's by switching off the output. So what's happening is the overall voltage kind of looks like it drops. So it's like Dave explained about how it in the limiting mode, it's like switching on and off, on and off, on and off. So on an average, the voltage on the output can kind of drop. So I need to find a workaround to that as well. So suggestions are really open on any of the parts of this particular project. So in the near future, I'll probably have version 4.0, which is going to be a lot more cleaner than what I have right now. So thanks for watching.